Welcome to a new video. In this video we will discuss the matrix diagonalization, and we will use this formula to calculate the power of a matrix. We have seen in the previous examples in the videos about the eigenvalue and eigenvector problems of a matrix, and this is the diagonalization where we use those eigenvalues and eigenvectors. So we will see how we can use this formula, and of course using an example where we see step by step the calculations and also verify these in MATLAB command window. Okay, before we jump to our example, let's give a brief definition of what is a diagonalization. So the definition goes like so. If you have an n by n matrix, it must be a square matrix. It is diagonalizable if and only if the matrix A has linearly independent eigenvectors. So what does it mean? Now, we can use this formula unless this is the case. Okay, so we have here the P, which is called the eigenvector matrix. We will develop that shortly in our example. And also the D here, where we need the eigenvalues in order to have the eigenvalue matrix. So the D is in general then given by this. So you have in the diagonal here the eigenvalues, and the rest of the elements of your D will be zeros. Now if you have a 2 by 2 matrix, then your D is also 2 by 2 because you have then two eigenvalues. In the matrix P, which will be then the eigenvectors in order as you have it here. For example, if you have here lambda 1, the corresponding vector, the eigenvector of that lambda 1, v1, must be also in the first column. And you can move on and then increase the dimension depending on the dimension of your matrix A. So now in order to calculate the power, so a to the power, let's say 5 or 10, you can use this formula. Only the matrix D is taken to the power k, and the other two matrices will be just multiplication. That's the power of diagonalization. In more precise terms, in mathematics, we say the algebraic multiplicity must be equal to the geometric multiplicity. Now, this is pretty difficult to understand maybe. What does it mean actually? That means actually the following. In other words, number of eigenvalues must be equal to the number of eigenvectors. For example, if you have a 3 by 3 matrix, you've calculated 3 eigenvalues, but you have only 2 eigenvectors. That means your matrix A cannot be diagonalizable, so we need to proceed in a different way to calculate the matrix to the power some value. That's the meaning of this condition. Okay. Now, why do we do the diagonalization? Now, we already said that, but let's see that in numbers. For instance, if we have this matrix D, which is given by this 5, 0, 0, 2, which is a pretty simple matrix, and let's say that we want to calculate the D squared, so D times D. What we normally do is, okay, we put this and we put it next to that, also the same thing, and then we proceed with the matrix calculation. So we do 5 times 5 plus 0 times 0. That means then the first entry will be here, 25, and then 5 times 0, and then 0 times 2, that will be then just 0. So you just proceed here, and the next one is 0 times 5 plus 2 times 0 will be here, 0, and then 0 times 0, and then plus 2 times 2 will be just here, 4. Okay, this can be tedious if you have here d to the power, let's say 20, but let's see what happens, because this is 25, this is 4. So this looks like, if you look at this original values in the diagonal, will be just 5 squared and 2 squared. Is this really the case? Now let's see. Let's calculate also d to the power 3. That means d squared times d, and effectively we already have a d squared from the previous calculation, just times d. Now you can now proceed again, and we get here 5 squared times 5, which is then 5 to the power 3, plus 0 times 0. And then in order to do the other things in the same manner, you get actually this result. So this looks like that we have the exponent here, the power, will be then just the power here and the power there, and the other two, which is our 0, will stay zeros. So we have now a very nice result. We can say in general that d to the power k, some value k which is positive, can be then k to the 5 to the power k and then 2 to the power k. That's it. And that is then pretty simple and fast in order to calculate the power of a matrix. So in more general terms, if you don't have the 5 or 2 or other values, we can use this where we have the eigenvalues. You can see here d to the power k is then equal to the lambda 1. In this case we have the 2 by 2, but this is also valid for 3 by 3 and other dimensions in square form. So we have then lambda 1 to the power k and the lambda 2 to the power k. So you only need your eigenvalues in your matrix and then to the power the k which you have here. So you can see that this matrix is pretty simple to calculate. Why can we write and why can we use this formula which is necessary to calculate the powers of a matrix using this method? Okay, this is the formula we have. If I want now, let's say a squared in a similar form as d squared, but now the a is given by this p times d times p inverse. So we have here the 3 matrices as a product. So we get again the same thing here, but now you can see here p to the power minus 1, so the p inverse times the p, that will be here actually the identity matrix, because if you have an inverse of a matrix times itself in the not inverse form, you will always have the identity matrix, like a 1 in the scalar operations. So you have then here p times d times the identity matrix times d times the inverse of the matrix p. But d times I is just d, so you will have here d squared. So that's interesting. So going from a squared, you can go to p d squared p inverse. So only thing that is to take into power, which is in this case 2, is only the matrix d, and the p and the p inverse will stay the same. Let's do another one. A to the power 3, which is then a squared times a. Now that means, now we already have that, so we just copy this p d squared p to the power 1 minus 1, so this is just p inverse. We can see here, because we again set here the a next to this one, so we just multiply that. But you see here p inverse times p is again I, that is our identity matrix, so that can be just multiplied out, and you can see here d squared times d will be this d to the power 3. Again, what you see here will appear here in the exponent of your eigenvalue matrix, in this case d. Let's do another one, which is then a to the power 4, so you have an a to the power 3 times a. Again, we take this result here and you put actually here this here, and you see again here the same form, so you can actually go on and then look at this in general form, but this is a to the power k, whatever it is always d to the power k here, and the p inverse will stay left and right. Okay, let's see it in real action with numbers, and we would like to calculate for this matrix given here 0 1 2 1, we would like to calculate a to the power 10. Now in normal situations you don't know anything about diagonalization, you should say, okay, let's do a times a, then you get a squared, then you do again a squared times a, you get then a cubed, and then you do a cubed times a, you get a to the power 4. Now that will take some time. Yeah, and you can make, of course, a lot of mistakes on the way, so that can be pretty tedious. And if this is a 3 by 3 matrix, that can be quite lengthy operation. Now, let's do that now using this diagonalization. So first the calculation, we start always with this formula where we define our determinant of a minus the lambda I equal to 0 in order to get the eigenvalues first. So first step is determine the eigenvalues. So you do here a, which is this, minus the identity matrix times the lambda, and then for that you take the determinant. That's actually shown here. So this matrix is this matrix. Now the operator for the determinant is you multiply this with this one minus the product of 1 and 2, and that's shown here. So minus lambda times 1 minus lambda minus 1 times 2, which is 2. Now if you work it out here, you get the lambda squared minus lambda minus 2. Now you can of course put that in the factors, so factorization, you get here lambda minus 2 times lambda plus 1 is equal to 0. So you have now here two solutions which are eigenvalues, or then lambda 1 is equal to 2. In order to make this 0, you get here 2, and you get here the second one is minus 1. Okay, now the eigenvectors for each eigenvalue. So we start with lambda 1 is equal to 2. Now we set up this equation where you have an augmented matrix, where you have a 0 vector here. Now we just do that specifically for the lambda 1 is equal to 0, equal to 2. Okay, now you just substitute here again in the same matrix, but then using the lambda 1 and identity matrix. So you can actually take this matrix and then put here lambda 1 and lambda 1. That's actually what I have here. Now you substitute really the number 2. So you get here minus 2 and then here minus 1. That's the next step. The rest actually stays the same. So you see here 1 and 2 here from the original matrix. It doesn't change. The only thing here is this one. And now we need to proceed such that we have here the 0. So we need to have a linear dependent form. Now we can do that by, in this case, right away by doing row 2 plus row 1. Now this will be then 2 plus minus 2 and minus 1 plus 1 and 0 plus 0. So all three terms will be 0 here. That's actually as we wanted. Now we can see that we have the second column here. There is no pivot. That means there's a free variable and we call this x2 because this is x1 column, this is x2 column. So we just name it or set it to t, which is then an element of the real values. And then we can look at this formula. We can see here minus 2x1 plus 1 times x2 is 0. That means minus 2x1 will be minus x2. So that means x1 will be half of x2 or 0.5 times t because x2 was defined as t. Now taking these together, you can make a new vector. That can be then like so, and then you have an x1 and x2, which is then 0.5 t and t, and you take t out, you will have 0.5 and 1. Okay, now we can now set up our eigenvector. In this case, the t can be anything except 0 for our real value. So you can say, let's take, for example, 1 and then set up our eigenvector for this lambda 1, which is then 0.5 and 1. In this case, specifically for t is equal to 1, but you can also take t is equal to 2 if you want, just this 2, 0.5 I mean, make this 2 and make this 1 and make this 2. That is perfectly fine, the result won't change. Okay, now going to the eigenvector for lambda is minus 1 for lambda 2. Again, the same procedure, you just substitute here the lambda 2. So you go here with minus 1, so that means then 0 minus minus 1. 1 minus minus 1, that means 1 here and 2 here. You see that the result here. And again, we proceed such that we have here a 0, 0, 0. So we have a linearly dependent form. In this case, we need to do a row 2 minus 2 times row 1. So we get here 2 minus 2 times 1, 2 minus 2 times 1, and 0 minus 2 times 0, which is all 0. Again, we have and we have no pivot in the second column. That means again this x2 is a free variable, again element of the real values, and we have x1 is equal to minus x2. Why? Because we have an x1 plus x2 will be 0, so effectively you can say x1 is equal to minus x2, or you can say it is minus t. Now taking these together in a vector form, you get here x1 and x2, which is then minus 1 and 1. And if you take here the t for in this case again 1, then you get v2 will be then minus 1 and 1. But you can also take as t is minus 1, it will be just 1 and minus 1. Again, this will not change the result. Okay, now we have everything what we need in order to go for the diagonalization. We have the eigenvalues and the eigenvectors. Okay, let's collect them here together. Eigenvalues and eigenvectors. Now we set up our eigenvalue matrix and eigenvector matrix. So this is D. We see here the lambda 1 and lambda 2. We have a 2 and a minus 1. That is important that you have it in the same order as you do it for the eigenvector matrix, because the matrix for the eigenvectors, we have here the V1 and V2. So don't do V2 and V1 because then everything is changing and screwed up. So we need to really go in the same order. Okay. So we just put this 0.51 here and minus 1 and 1 in here. So we have our D and the P. But we also need the inverse of P because we know that from our calculations of the diagonalization. So we need to go to the P inverse, and for a 2 by 2 matrix we know this formula. So you do 1 over the determinant of P and times this element, which is the swapping of these two elements in the matrix P, and you reverse the sign here, these two elements. So you actually make this a +1, -1, that's actually shown here, and you swap the places of this 0.5 and 1. That's shown here. Now, what is the determinant of P? How is the formula working? Now, this is 0.5 times 1 minus the product of these two. That's shown here, and that will result in 1.5. So we get here 1 over 1.5 times this. Now, 1 over 1.5 is actually 1 over 3 over 2, which is then 2 over 3 effectively as a factor, as a fraction, I mean, and then you have this expression for your inverse of matrix P. Now we have our necessary elements to set up our equation. Then we can use the expression for the powers in the diagonalization form, because we have the P, we have the D, and we have the P inverse. So we need to go to the a to the power 10. Okay, now let's do that. We know that the 10 will only be appearing in the exponent of D, so it means this is only what we have. Now we can then set it up like so, because you only need to do that for the eigenvalue, which is then 2 to the power 10 and minus 1 to the power 10. So it will then appear like so. So in detail, you see here the P inverse and the P and then D here to the power 10. Now if I now shift this to 2 over 3 all the way to the left, because that's convenient and easy to follow what's going on, we can put this 10 here in the exponent for 2, and also here minus 1 to the power 10. So 2 to the power 10 and minus 1 to the power 10. Important here is that you need to put this in the parentheses, otherwise you get here minus 1 to the power 10, which will then stay minus 1, but it should be actually 1, because this is an even number. Okay, now we need to work out the matrices. Let's first work out this. 2 to the power 10 is 1024. This is just 1. Now we can work out these two matrices. So you do here 1024 times 1 plus 0 times minus 1, and then 1024 times 1 plus 0 times 0.5. So you proceed like so. So you don't do actually much with this one. And you go on, and then you also have it here. The next step is to calculate the matrix calculation of these two matrices. So you do 0.5 times 1024 plus minus 1 times minus 1 will be then 513. And you proceed like so again. This row times this column, and then this row times this column will be appearing here, and this row times this column. Again, you will have this 2 over 3 in front. Now you will process this 2 over 3 with these four values, and you will end up with this matrix, which is then 8 to the power 10. Now this is indeed the value we need to have for this example. Okay, let's bring everything here together. Eigenvalues, eigenvectors, determinant of the matrix P, the eigenvector matrix, eigenvalue matrix, the inverse of this matrix P, and this is the end result for 8 to the power 10. Now let's see that in MATLAB. Now we define here our matrix, given here. That's also shown here. Now we calculated with this command eig, in parentheses a, the eigenvalues. Those are minus 1 and 2. But those are exact same as we have it, of course in a different order, but doesn't matter. And I define also here my eigenvalue matrix D in the same order as we have it. So 2, 0 for the first row, and then semicolon 0, minus 1 for the second row. So we have it exactly as we have it. Okay, now next part I will define two vectors, v1 and v2. Those are these two vectors, so 0.5 semicolon 1. And then v2 is minus 1 semicolon 1, that's this one. Now I make this matrix P, which is then v1 and v2. That is this one, you can actually see that here. So I make the eigenvector matrix that's shown here, which is actually also shown here. And then I determine the determinant of P, just to show you that it is indeed correct. So we see here the 1.5 appearing, and this is the exact same as there. And I calculate also the inverse of p, which is then using this command inf of p, and now you get here the result, which is then here 0.6667, which is then 2 over 3 actually, so 2 over 3 times 1. Again, this one also, so 2 over 3 times 1, and now here minus 2 over 3, which is then also here, and then here 2 over 3 over 2, which is then 1 over 3, which is then 0.333, etc. So this is also all correct. Okay, the next one is about the calculation with this a to the power 10. Now if you do that directly in MATLAB, you get this result. So 342 and 341, etc. So actually, yes, we have it, but if you do it with our calculations with p d to the power 10 and times the inverse of p, you get the exact same result. So these two results are exactly the same, and this is also what we have calculated. Alright, it was our example considering the diagonalization of a 2 by 2 matrix. We have calculated our eigenvalues, then the eigenvectors, and we set up our eigenvalue matrix D, eigenvector matrix P, and then also calculate the inverse of that one. And we use the multiplication as we have it for the formula of the powers of a matrix. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video.